So welcome to SAE India's SUPRA 2014 webinar training session day 3. I am Apur Bapat. I am working with Altair Engineering. I am basically working in Altair Engineering Pune office. So in today's session, we are going to see how to perform torsional rigidity and bending stiffness and how to calculate these two values using HyperWorks. I guess Mehak has explained you the reason why we want to calculate it. Sometimes people used to calculate or perform the analysis of front impact, side impact and rollover. But if you are using impact attenuator, then the front impact analysis is really will not help you to design a better roll cage. But if you follow the rules specified in the rule book of SUPRA 2015, then your roll cage or chassis is definitely quite a safe. But as you all know that if you are able to reduce the weight and maintain the stiffness or the rigidity of your chassis, will help you to get an additional points in endurance or either in cost or in all the different aspects of the SUPRA events. So in today's session, we are going to see how to import a CAD model in Altair HyperMesh. Then those who don't have a CAD model ready with them, I'll show how to create 1D line structure of chassis in Altair HyperMesh. Then how to perform 1D meshing. Then how to create a solver deck for OptiStruct, that is the solver in Altair suite. Then how to view the results in HyperView of displacement or stress values. Then how to calculate the torsional rigidity and bending stiffness. That is the most important part of today's session. So as we have somewhere around 300 plus attendees, so it's very tough to answer each and every question. So, but I suggest you to keep writing the questions in the chat window so that at the end we can have the database of your questions ready and we can answer it later on. So let's start with the opening of HyperMesh. To open the HyperMesh, go to Start, All Programs, HyperWorks Student Edition, and click on HyperWorks. Once you click on HyperWorks, it will open the GUI. Once it's opened the GUI of HyperWorks Student Edition, it will ask you for the user profile. So those who are using HyperWorks Student Edition 13 and 12, select the user profile as OptiStruct. Those who are using the HyperWorks Student Edition version 11, select the user profile as Radius Bulk Data. So select, as I am using HyperWorks 13, so I will select user profile as OptiStruct. This the user profile selection will help us to generate the required templates to solve the model using that particular solver. So let's first I will quickly explain you the GUI of HyperWorks Student Edition 13. So these are at the top, you will find the drop down menus. These are the quick access icons which are available in these drop down menus also. During the training you will see the use of different icons. This is the main menu where there are 7 different pages to access different panels as per the name of the pages. So geometry page contains the geometrical panels, 1D page contains the 1D panels, 2D page contains the panels related to 2D, 3D page contains the panels related to 3D, analysis page contains the panels related to the analysis, tools related to the different operations you can perform in HyperMesh, and post is the post page will help you to access the different panels available for post processing. So as I have already told you that I am going to show you both the options. That one way is if you have a line data ready with you, roll cage line data ready with you, how to import that, and if you don't have, how you can create it. So first I will show you how to import a roll cage CAD data. So go to the import button. Select import geometry. Select the file type as IGES. Browse the file. Then on the bottom you will see import options. This is the scale factor. Sometimes in CAD software you create the files in either meter or inches or centimeter. But my suggestion is, while you are importing the file in HyperMesh, always import the file in mm, so that it will be easy for you to provide the other required details to perform the analysis and to view the results also. So this scale factor help you to import the model in mm. So as my model is already in mm, so I will put the scale factor as 1. But if my model is in inches, then I will put the scale factor as 25.4 and then I will click on import. So while importing, it will scale it up and make it into mm. So I'll click import to import the geometry of roll cage. So you can see this is the roll cage structure of the SUPRA vehicle. Also, this in this training, whatever the models or the values which I am going to use is just an example. They are not the exact values or the exact structures. They are just examples. So it depends on you how you create and use the values. So basically this training is to explain you how to perform the analysis. This training is not that how you to tell you how to do the analysis. Sorry, how the values can be put to perform the analysis. This value is not for this training is not for that. So in this way you can import the IGS file in HyperMesh. You can press Control left mouse button to rotate the model, Control and right mouse button to pan the model, and Control and scroll up, scroll down to zoom in, zoom out the model. Now I will show you how to create a roll cage in HyperMesh itself. So to create a roll cage in HyperMesh, I need the reference point first. So I will create a reference node for that. So go to Geometry, Nodes, select the first option, that is XYZ. Enter the XYZ value as 000 and click on Create. Press F on your keyboard to make this fit to screen. So you can see a node on the screen. Then as per your dimensions, create the other points. So I am going to create a roll cage length of 100. First front box will be of 100, 100 and 100. Press F to fit to screen. So this is the front portion of my roll cage structure. With regard to this, I will create the lines. So go to Geometry page, Lines. Select the second option, that is Linear Nodes. Select two nodes and click on Create. Similarly, click on Create and create all the 4 lines. So in this way I have created a line structure here. Then for the further use, I will use Shift F4 to enter to Translate panel, or you can go to Tools, Translate. On Tools page you will find a Translate panel, that is on the third column, third row, and we will select the lines. Want to translate in Z direction to a distance of 250, but the duplicate lines and translate. So I have translated these lines. I will cut it down to 100. The distance is looking very much. Now it's good. Now I will translate this further, this particular line in y-axis to 25. Press F8 to enter to nodes panel. We'll create two nodes. Delete these lines. From F2 you can enter to the delete panel. Then again on geometry, lines, we'll create the lines. Shift F2 is to clear the temporary nodes. Similarly, we can create the lines from this structure to this structure. So my front portion is done. Now I will again go to Shift F4, Shift left mouse button and select these lines. In Z axis, I will translate it to 400 mm. Again lines, duplicate original component. It's also looking very much, so I will reduce it to 100. Then again F8, select the lines and create the nodes. Lines from this to this, create, 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 create. Now I will transfer this to upside, so Shift F4. In y-axis, let's say 100, but line duplicate. Again F8, this node, then this node to this node. You can see it is not that much wider, so I can widen it down also. So how you can widen it to certain extent, that I will show you. So press F4 from your keyboard and find the center node of these 2 points. Then you can go to Tools, Scale option, select the lines which you want to scale, select the node and uniformly at 1.5 times. So this has scaled to all the axes, so I can't use this option. So again Shift F4, this to x-axis, let's say 10. This similarly this one, similarly this one. Now I want to delete these lines. Shift F2, clear these nodes. F8, create the nodes on this so that I have a reference to create the lines from this end to this end. So in this way you can create the geometry and edit it later also in HyperMesh itself. So this looks pretty well. Now I will translate this to y-axis. duplicate, F8, create 2 nodes, and from here to here, here to here, from this end to this end, from this end to this end. So base structure is ready. If you want to create a cross members, you can also create a cross members here. If you want to create a mounting member, that is also possible. Create 5 nodes here, 5 nodes here, then enter to the line. This is the mounting member. You can have a cross member for this too, and a cross member from here to here and here to here. These lines are not intersecting, so I will go to line edit. Then if I want to create a roll hoop here, so how can I do that? Go to F4, create a node in between these, find out the distance, it's 70, go to circle along z-axis to this node, radius will be 35, angle to 180 degree, and create. Sorry, it's 70 and create. So this is the roll loop. Similarly, you can create the front roll loop also. Now I will use these lines, duplicate original Z component, to translate it on the back side. Again F8, 2 nodes, lines, so if you want to create the cross members, you can create it here like this. You can also create a cross member here and a cross member here, and you can also join from this to this, this to this. If you want to create a mounting member here, you can also do that. F8 to put one more node here, then from this to this. So in this way I have done with the roll cage. So in this way you can create a roll cage in HyperMesh itself using the different options available in HyperMesh. So now let's move to the next, that is how to perform the 1D meshing. Okay, so now we will see how to do 1D meshing on the roll cage structure. So before that we will go to HEdit and So there is a process for that. To perform the static analysis in OptiStruct, there is a process called MHPCLL, where M stands for material collector, H stands for hyperbeam, P stands for property collector, C stands for component collector, L stands for load collector, the other L stands for load step. I will explain you what are these. So material collector, in material collector we provides the material information like the values of E, nu and rho, so that my software will understand what type of material you are using. In hyperbeam we will provide the cross sections which we are using, like we are using the circular hollow pipes or circular hollow cross section or square hollow cross section. In property collector we define which type of meshing we are going to use, either 1D, 2D, 3D. Accordingly the solver will choose the templates to solve that model. In component collectors we assign the property and material, so that whatever meshing is done in that component will get the proper material and property, because the meshing will be going for the in the solver. So only the elements will get solved. Geometry will not get solved in the solver. Then in load collector we define the loading conditions, like what are the forces, what are the constraints, the magnitude and all. In load step we define the type of analysis what we are going to perform, whether we want to perform linear static, non-linear static analysis, multi-body dynamic simulation or modal analysis. What type of analysis we want to perform we define in the load step. So let's follow the process. So first we define the material. So to define the material, click on material collector icon, or just right click on the model browser, go to create material, enter the material name as steel, select a color, card image matte 1, E as 2.1 e to the power 5. We are by default taking the values of steel. So if you want any other values, you can take that, and providing the value of nu and rho. Then material is done. Now you can again go to create hyperbeam. So to create hyperbeam, you have to go to 1D page. On 1D page you will find a hyperbeam panel. Select the standard section, the third option. Select hyperbeam as the standard section library. Select standard section type as thin walled box, thin walled tube, to create the hollow circular cross section, and click on create. So once you click on create, it will redirect you to a new GUI, which is the hyperbeam GUI. On the left hand side you can see it automatically calculates the area, centroid, moment of inertia, centroidal principle, everything it has calculated automatically. So what you have to provide is the outer radius. I am taking an example like 12.5, and inner radius in mm, So this also I am taking as 9.5. So I have taken the inner and outer radius as 12.5 and 9.5. So my thickness will be 3 mm. Now to go back to HyperMesh, click on the model view, which is at the left hand side top corner. Just below the model you will find model view icon. Just click on that. So on the model browser you can see a beam section is being created which contains the hyperbeam values. So click return. Now as per the formula, my next thing is to create property collector. So now I will again right click, create property. So I will enter the property name as 1D roll cage, define a color, card image P beam, then material steel, then the beam section tube section. So once you select the beam section, you can see it takes all the required values like area, polar moment of inertia and radius of gyration. So it has taken all the other values which is required to define a cross section, IXX and IYY. So it has already taken from the hyperbeam. So my property is done. Now I will update the property with the component. So to update the property, go to component collector, select the radio button as update, click on comps, select the component, from no property toggle it to property and select the property as P beam or the 1D roll cage which you have created earlier and click on update. So once you click on update, the component is updated with the proper material and property which we have defined earlier. So now we will do the meshing, the 1D meshing on this roll cage. So to do the 1D meshing on the roll cage, go to 1D page. On 1D page, select line mesh, which is on 4th column, 1st row. Select all the lines. Select the element configuration to bar 2 because in bar 2 there are beams and bar element configuration. So select bar 2 element configuration. Select the property which we have created earlier. Enter the element size as 5 and click on mesh. Click return. Make this to current component so that meshing will go to the current component. So my meshing is done, so I will off this geometry. Now you can see the elements. I will show you the elements in 3D representation. So you can see the elements in 3D representation now. Now many people from here goes absolutely wrong till the color plot which you get in the post processors. Why? I will tell you. They don't check the connectivity of these members. So if you don't check the connectivity of these members, that means the force whatever you are applying at the front or rear and whatever the constraint you are applying at the front and rear is not getting transferred through the complete roll cage. That means the analysis is not correct. So now we will, before performing anything, we will first check the connectivity of all these joints and correct it before going further. So to do that, press Shift F2 from your keyboard and select all the nodes of the joints. Of only the joints, select the nodes. Left click, drag the mouse and select. Most of the analysis software doesn't provide this option to check the connectivity of the members. So if the members are not connected, then your analysis or whatever you have applied the forces and constraint will not give you the proper results. It's not about getting the color plot, it's about the engineering to get accurate results, which has to be logical. So the results, if they have to be logical, the connectivity has to be proper. That is the most important thing. So even though it takes time to perform these things, still they are very important to do it. So select all the nodes, all the joints, select all the joints where the nodes select all the nodes on the joints. So you can see I have selected all the areas where the two members are connecting and click on add. Now before going further, what I will do is I will press F2 from my keyboard and delete all the elements on the nodes. Just select and delete all the elements which comes in the joint. You can see there is no connectivity here. These two elements are not connected. So just delete all the nodes, all the elements which is joining at the corner. We will again create the nodes. So why I am doing is to make sure that connectivity is proper. You can see here the connectivity is not there. You can also see the connectivity is not there. So why this is so? Because of the line data, the geometry which you have imported is not properly connected. So that's why the elements also not connected. That happens to each and every tool. Even if you solve in any CAD software, still the problem will be same. You will not find the meshing connected properly. So this step is the most important step in the complete analysis process. That checking the connectivity and maintaining the connectivity first and then performing the analysis. So you can see here the joint is not there. So I will delete the nodes. Sometimes you may ask, like, if we have a proper connected lines, then also we need to do this. I'll say yes. Even though if you have a properly connected line, still performing this and ensuring that your elements are connected properly is always good. instead of solving a wrong model and getting a wrong data and going further with the wrong data and analysis which you have performed. So I'll again repeat that analysis is not just getting a color plot. If you want to getting a color plot, it hardly takes 15 to 20 minutes to get a color plot of all the analysis which you think you can perform on a roll cage structure. But that is not engineering. This contest is all about the engineering. So it has to be correct and proper. You can see here there is no connectivity. You can find two different nodes. So in this way, you have to first delete all the elements and then you have to create the elements again, so that you will be sure that your roll cage is connected throughout. There is no connectivity issue, which is the most important thing. So as I have deleted all these elements, now I will start creating them one by one. So to create the elements individually, go to 1D page. On 1D page, you will find the bars panel that is on second column, first row. Select the property, element type C beam, that is component of beam. This orientation means the cross section which you have defined should align to which axis. So if your length is in XY plane, then the cross section should be aligned to Z axis, so that you can define all the three dimensions. So if I am going to create element along this axis, that is in Y axis, so the cross section should be, orientation should be Z axis. Similarly, this is X, but this is Y, so I will change the orientation to Y. So it has to be properly oriented, otherwise you will find an error of the orientation. So this is Z, so I have selected Y as the orientation, and once it's come in XY plane, I will select Z as the orientation. Always select the perpendicular, whatever there is perpendicular to that. So first I have to create a node in between, and from here to here I have to create a connected element. Change it to Z. So I have a model in which all the nodes are properly connected. So I'll not show you how to connect all the nodes. So in this model, all the nodes are properly connected, but the process will be same. You have to follow that process itself. So I'll go to update the component, update. So now again I will see the cross section. So now in this way all the joints are connected, which is the most important point before performing the analysis. So if you have any queries, feel free to ask. Now I have done, according to the formula, I have done with M, P, C, these thing and meshing. Now I will start with the load collectors. So I'll again make this to I. Now to define a load collector, go to load collector icon, enter the load collector name as force, change a color, and click create. So on the model browser you can see a load collector is defined. Now we will apply the force on the model. Right now I am going to show you how to solve torsional problem in HyperWorks. So go to analysis. On analysis, click on forces. Now the question is where to apply the forces. So you should apply the forces at the suspension pickup points, or the points where you are going to mount your suspension on the chassis. The points may be different for different roll cage according to your requirement. So whatever points I am selecting are not the fixed points where you have to apply the forces. The forces has to apply where the joints are there, where you are going to join your suspension to the roll cage. So I am assuming I am going to join my suspension to these points. In z-axis. Now about the magnitude of force. Magnitude of force depends upon you, that how much torsional force you assume or you calculate will apply on the roll cage structure. So that entirely depends on you. I am assuming that a 10,000 Newton of force will distribute on the one end and a negative 10,000 will distribute at the other end and will create a torsional force on the roll cage. So I will create it here. Similarly, at the other ends, I will apply a force of minus 2500. So this is the torsional force which I have applied. Now I will apply the constraints. Constraints means so go to load collector icon again, enter the load collector name as SPC. SPC stands for single point constraint. select a different color and click create. Now we will apply the constraint on the model. So to apply the constraint on the model, that is the reaction force. So what in torsional analysis, what we are going to do is, we are going to hold a chassis either from rear or from front and try to twist it. So torsional rigidity tests can be performed either on front section or the rear section. So the process will be same, but it depends on you how you want to perform. But you have to perform in both the direction, that is in clockwise direction and anti-clockwise direction. Like one side up, then another side down in this way. If you are performing the front torsional, or you can perform all the four, that is front clockwise, front anti-clockwise, and rear clockwise and rear anti-clockwise. So you can perform all these four analysis. That is also possible. So now I will constrain it. So to constrain it, go to analysis, constraint. To constrain it also, we will select the suspension joints where the suspension is going to mount on the roll cage. So I am assuming my suspension is going to mount on all these 8 points. I will click on create, and I am constraining to all the 6 degrees of freedom. That is DOF stands for degrees of freedom. DOF 1, 2, 3, 4, 5. In DOF 1, 2, 3 stands for degree of freedom along X, translation along X, Y, Z axis. And DOF 4, 5, 6 means rotation about X, Y, Z axis. So I am fixing all the 3 translation and all the 3 rotation. So you can enter to a load collector panel, a load collector icon from this icon and create the 2 load collectors, forces and SPC. Now the last step is to define the load step. So I'll again go to analysis page, and in analysis page I will click on load step. I will enter the load step name as torsional, select the type as linear static, check the box in front of SPC and load, select SPC in front of SPC, load in front of force, and click on create. So I have defined a load step. So my process is completed, that is MHPCLL. Now I will save this file and solve it using OptiStruct. So I will go to file, save as model, save this file, then go to analysis, OptiStruct, select export option to all, run option to analysis, keep the memory option as default and click on OptiStruct. So once you click on OptiStruct, it will start the solver window. As you can see, analysis completed message has appeared. If you are finding any issue, then please send us the screenshot of what error you are getting so that it will be easy for us to help you out. So click on results to view the results in HyperView. So this is the GUI of HyperView where you can view the results. So click on contour icon where my mouse pointer is currently. Select the result type as displacement and click on apply. So this is the maximum displacement which is coming. I don't need the maximum displacement which is coming to calculate the torsional rigidity. I need the displacement at the point of where the forces is applied to calculate the torsional rigidity. So how can I do that? I will go to measure icon. In measure icon I will add one more option, and select the relative displacement, multiple nodes, and select all the nodes. All the 8 nodes where I have applied the forces. Check the box in Z because I have applied the forces in Z, and click add items. So this magnitude is global displacement and this is the Z displacement. So you can see the, oh, I missed a point. So you can see the displacement values are almost same across all the 8 points, like it's 5 here in positive, 5 in negative, 5 negative, 5 positive, similarly 3 positive, 3 negative, 3 positive, 3 negative. So torsional rigidity means the unit of torsional rigidity is Newton meter per degree. So now to calculate the deflection or the degree of how much deflection is happening, what we have to do is add these 2 points. Like I will tell you how to calculate the torsional rigidity. Add angle of deflection. To calculate angle of deflection, you need to subtract the Z deflection of one point with the Z deflection of the parallel point. So 5.183 minus of 5031 will become plus 5.031. So the sum is coming as 10.24 radians. This value is coming as radians. Now to find the angle between this, I also want to find the distance between the force applied. So I'll again go to HyperMesh. To find this distance, press F4, select this node, it's coming as 380. So angle of deflection is 10.214 divided by 380. That is 0.0268 radians. Now to find it in degrees, we need to divide this with 3.14 and multiply with 180. So it's coming as 1.5 degrees. So my angle of deflection I have calculated. Now we have to calculate the torque applied. So the torque applied can be calculated as total force applied, that is 20,000 on all the 8 nodes, the total force what you have applied, divided by sum of all the distances. So I will find all the distances, like that is average of all the distances. So this is 380, 380. This is 783.677. Sorry, this is 495.556. then this to this is also 495.556. This distance is in mm. So again I will open the calculator. So I will calculate the average of this 380 plus 380 plus 495.556 plus 495.556 divided by 4. This is the average distance in mm. Now to calculate the torsional stiffness, we have to divide this value with the force applied. So I will again put 20,000 divided by 437.778, which is coming as 45.685, which is in Newton mm. So now I will divide this value with the angle of deflection, 0.0268. This is what my torsional rigidity is coming. So by applying the first case, my torsional rigidity is coming as Newton mm per degree as 1704. If you want to calculate in Newton meter per degree, so you just multiply this with the required multiplication factor to get the torsional rigidity in Newton meter per degrees. So this is what you have to calculate, and in this way you can calculate this. So if you have any doubt, feel free to ask. Now let's move to the next point. So I will turn off this and off this. Now the next point is how to calculate the bending stiffness. So we will apply the bending force. So again I will go to load collector icon, enter the name as bending force. Select a color, create, go to analysis, forces, select the nodes, where I am going to mount my suspension on the chassis. Whatever force you want to apply, apply it. I have missed a point here. So I have applied a bending force here. In bending also you have to apply or calculate for two different forces. One is downward, the other one is upward. Then create one more load collector as bending SPC. Define a color. Go to analysis, constraints, and fix the rear. Say create. Now I will define the load step. Bending, type as linear static, SPC will be bending SPC, load will be bending force, create. I will again save the file. Analysis, OptiStruct, and again OptiStruct. So my analysis is completed. Now I will see the displacement. At the point where I have applied the forces. Here for bending stiffness we can take the global magnitude. It is not required to take particularly the Z magnitude. So I'll open both. So these are the global magnitudes of all the 4 points. I will take the average of all these 4 and divide force by the average of this, and that will be my bending stiffness. So I will first take the average of these all values. (8.5) plus 8.6 plus 5.2 plus 4 plus 5.6 plus 5.7 plus 3.5 plus 3.5 divided by 8 is the average, and I will divide the total force I have applied is 20,000 divided by 5.74. This is what my bending stiffness in Newton per mm. If you want to calculate in meters, so you can calculate in meters by dividing with the appropriate scale factor. So you can see in one single file I have solved 2 different cases. One is bending force and the other one is torsional. In the similar way, you can see in one single file I can solve multiple cases like torsional front clockwise, torsional front anti-clockwise, torsional rear clockwise, torsional rear anti-clockwise, then bending front clockwise, bending front anti-clockwise, bending rear anti-clockwise, and bending rear clockwise. So you can solve whatever case you want in one single file, and I will show you the results of all these. Also we will see how to check the load path, whether it is correct or not, how to check that. So first we'll see the animation plot of this. So you can see if I turn the wireframe thing on, stop. So you can see the bending is happening, the torsional thing is happening on this particular roll cage. As I applied, this roll cage is very weak and applied very high forces on this. That's why this value is very high. Generally, this value doesn't come that high. Then we'll see the animation of bending. Actually, I have taken the values of torsional. I have to take the values of bending. So the same way I'll repeat the process again. I have to take the global magnitude and average of all these, like 15.8 plus 15.8 plus 15.9 plus 15.9 plus 8 plus 8.1 plus 8 plus 8.1 divided by 8, so it's 11.95. So 20,000 divided by 11.95. This is what 1673 is the bending stiffness. You have to change the subcase from here. This is torsional, this is bending. So here I can show you the analysis of results of different analysis. So if I on the displacement value, this is the maximum displacement torsional, clockwise and anti-clockwise, rear, clockwise and anti-clockwise, bending front, clockwise and anti-clockwise, bending rear, anti-clockwise and clockwise. Now I will show you the results of stress and we will check the load path. So you can see the load is coming from this end and is directing towards this. So the red color doesn't mean it is failing. You have to check the maximum stress value is, it's very less. So that doesn't mean it's failing, but this point is in high concentration. The red color means the load distribution is in this particular direction. Similarly, if I change the value, it goes to the second half for the anti-clockwise. For bending, these two, the blue regions are not taking any forces. Then torsional rear, then bending. So in bending as well as in torsion, this member coming as the weakest member because the maximum force stresses value is coming here. So bending front anti-clockwise, then bending rear and bending rear clockwise and anti-clockwise. So we can also see the animation. Go to deform. I will show you all the animations. So this is torsion, clockwise and anti-clockwise, rear, clockwise and anti-clockwise, bending, clockwise and anti-clockwise, rear bending, clockwise and anti-clockwise. So you have to understand the load path also and which members are coming in the bending, as you can see by the animation, and how much bending force is coming on this, that also you have to calculate or check, and accordingly you have to decide that whether this portion is safe or not. So as in last 2 days, what Mahek has explained is the member becomes weak if it's come in bending. So if it's coming in tension compression, then that is not a big issue. But the members, if it's coming in bending, that is an issue. So for designing your chassis, these two parameters are the most important. Other than that, it is not like solving this model once and finalizing your final roll cage. Have a base chassis ready with you. Keep on performing the analysis and keep on adding and removing the different connections of your on the roll cage, and then finalizing the values will help you to design a much lighter and stiffer chassis which will withstand the complete loading condition. So that is the most important thing. So if you have any queries, feel free to ask. So in this way, I have ended with this today's session. Tomorrow I am going to discuss about the 3D components. That is how to perform the analysis on knuckle, hub. Also, tomorrow I am going to show you how you can create impact attenuator geometry meshing on HyperMesh. And day after tomorrow, I am going to show you how to perform the dynamic analysis on impact attenuator. That is the front impact analysis in dynamic condition. This is static condition. We will go to see the dynamic condition the day after tomorrow. So if you have any queries regarding the today's session, feel free to ask. What I personally feel is the front impact and side impact and rollover analysis will not help you much in designing the roll cage. But if you still want to perform these analysis, you can go through the videos available on YouTube and the material available on Altair website. So to know the process of how to perform the 1D analysis on the roll cage. Sorry, how to perform the front impact, side impact, rollover analysis on the roll cage. So in this way, I have ended with what I am going to discuss in today's session. Thank you for attending this session. You can ask your queries to us via edu-support@india.altair.com. E is small. So thank you very much for attending this session.